just to refresh from last class, the reason why we need to do regression analysis, why we need these type of statistical tests in economics, is because we cannot do you can't do experiments like you can in other fields. Obviously, you can't separate the U.S. into two randomly, give one half expansionary monetary policy, the other half contractionary monetary policy. So because of that, we need to develop these statistical tests in order to try to determine what the effects is. And it's, on the one hand, it's confirmation of our theory to prove what the effect is, to provide evidence in favor of our theory or to disprove our theory. But it also allows us to estimate what the actual effect is. So this right here is how we ended class with an output from Stata for a simple regression. So we regressed the test scores, the average test scores for students on the student-teacher ratio in their class. These slides come from Stock and Watson's Intro to Econometrics textbook, and throughout that book, the running example is student test scores and student-teacher ratio. Can anyone from last class remind me what these two numbers, these two coefficients represent, what they mean for us? Not exactly. So, basically what we've estimated is that if the student-teacher ratio was 0, that the average test score would be 698.9. Obviously, that makes no sense because you need at least one student in the class. But sometimes our data is on both sides of 0, it's positive and negative, and in that case, the y-intercept would make sense. But because this is the line of best fit for two variables, it's so important to know where it's going to cross the y-axis so you can actually plot the line. The negative 2.28 times the student-teacher ratio means that for every 1 unit change in the student-teacher ratio, that we're going to see the test scores drop by 2.28 points. So we see basically there's a negative relationship between the student-teacher ratio and between student test scores. Now, theory would suggest that this outcome makes sense, that the more students there are in the class, the less attention the teacher can pay attention to each student, the less they can answer questions, are able to tell if they're struggling or not. So the fact that it's a negative number that confirms our theory. And then the the fact that it's 2.28, that's our estimation of what the actual effect is. What else I want to say? The p-values, I'll hit that again. The probability that the coefficients that we estimated, that these two numbers are due to random chance. That's what the p-value is. In this example, p-value is 0. So there's a 0% chance that these are due to just random error. Suggesting that both of those coefficients are statistically significant, meaning that this is a good model or a good estimate. Can you guys see any problems with using just test scores and student-teacher ratios? What? What was that? You think other things might affect the test scores just besides the
demographics?
Studying for a test, maybe?
Funding of the schools.
That's right. There's a lot of other things that affect test scores than just the student-teacher ratio. And that's why when we design these models, we need to use more than just one variable. So there's two statistics that we can use to to understand the, I guess, how well the regression line fits the data, or how much of the data we can explain. The first, and the one that we're going to use, that you'll likely be using for your paper, is the regression R-squared. So that measures the fraction of the variance of y that's explained by x. So in this case, the amount of, I guess, the variance of the test scores that is explained by the student-teacher ratio. There's no unit for R-squared, and it's between 0 and 1, and it can be 0 or 1. 0 is no fit. It's a terrible model. You don't explain anything. 1 is perfect. You've explained absolutely everything. Basically, any model you're going to run isn't going to be either 0 or 1. There's going to be at least some explanation. But if you picked basically like your two variables were the same data, it would be 1 because the one perfectly explains the other. So if you plotted unemployment and did a regression, it'd be 1 because obviously it explains the change. The other measure of fit is the standard error of the regression, and it measures the magnitude of the typical regression residual in the units of y. So that's that u variable we mentioned, that was just like the error. Obviously, you want the error to be as low as possible. And that's to back up, that's the distance between the predicted y value from our model and the actual y value. Since you're not going to be calculating R-squared by hand, you don't need to memorize that formula for R-squared. But I wasn't going to delete it off the slide. So basically, just what you want to remember is your R-squared is going to be between 0 and 1. The closer to 1 you get, the better. Based off of what you're studying, a good R-squared is different. So if you're studying wages, a lot of the models I run involve the impact of regressions on, or impact of regulations on wages. It's going to be low. Like your R-squared is going to be like between 15 and like 25%, and that's considered good. If you're looking at other things, you're going to want to be much higher. You're going to be maybe 60% or 0.6 or 0.8. For that, you have to get a feel of the literature. Just look at the outputs of other people that have been like doing research in the field. Look at a couple of their papers and see where there are squareds at, and that's a good hint of whether your paper's doing well or not. Your model's doing well. Yeah, that's all I'll really say about R-squared. So for our example, our R-squared is 0.05 for the test score and the student-teacher ratio. You guys think that's it's a sign that our model is doing well, that it's a good predictor?
Yeah.
I think the sarcasm is going to come through on the lecture capture.
Oh.
But yeah, you can tell by the scatter plot just how spread out all these are right here, that it's not going to be a good fit. So in this case, only 5% of the change in the test score can be explained by the student-teacher ratio. Obviously, like you guys talked about, this makes sense because there's a lot of other things that impact grades. The amount you study, how much money the school districts spend, all the different demographic characteristics. So to solve for this, what we're going to have to do, oh, never mind. I guess we're going to shift into the assumptions first before we talk about the solution. If you want to use a statistical model to try to test something, there's a few assumptions that you're going to need to meet. You're going to have to make sure that these hold. If not, or if you can't make a decent argument that they do, your model isn't going to be able to accurately estimate whatever relationship you're trying to estimate. So there's three main assumptions for ordinary least squares that you need to make sure, I don't know, you got to check those boxes before you can use it. And it's both how your variables are related to each other and the way in which you've collected the variables. So there's our very basic ordinary least squares equation. The first assumption is the conditional distribution of u given x has a mean of 0. What that means is that the error term, the errors between your line of best fit and the actual points, has a mean of 0. So you have a bunch that are below and a bunch that are above your line. So basically, you're not constantly overestimating or underestimating. If we go back to this line, that's what it's saying is there's a bunch of points down here and a bunch of points up here. If all the points were up here and there are only a couple down here, then it would fail the first assumption. Because you're almost always, the points are up here, you're almost always underestimating what it should be. You want those errors to be what they call randomly distributed. So they're on both sides of your line of best fit. The next is that the x and y are independently and identically distributed. If this holds that they're independent, that means not one. If they're independently identically distributed, that means this is, okay. This is true if x and y are collected using simple random sampling. You don't want it to be, I don't know, I say as if there's several different ways to sample in statistics. You can go, obviously the first one's like convenience, like you can literally stand outside of Schwab and just poll people. And that's gonna go based off who's easy, who happens to be walking by. What you want to use is what they call simple random sampling, is to get a whole group of people and to really randomly choose the ones you select. So that way it's representative of the entire body. If you pick, say, the first 20 people out of the building or even the first 20 names on the list, it's not going to be truly random. So you're going to have problems relating what your outcome is to the entire group, because there may be characteristics that are making those people go first. Their characteristics may not be the same as everyone else in the entire group, so you want them to be randomly sampled. And finally, the large outliers in X or Y are rare. The math term have finite fourth moments that basically it's just the outliers are rare because they can really skew your results. It's similar to mean and median. In statistics, when you have data that's skewed in one direction, say you're looking at wages. It's usually skewed like that, where there's a few people over here that earn a ton. That's going to draw the mean over here, while the median is going to be back there. So your median is going to be a better measure of average, because it's not affected as much by the extreme outliers over there. It's the same thing with your coefficients in your models. If you have large outliers, they're going to be drawn out in that direction, and it's not going to be a good representation of what your data actually says. So to give you an example, you've got one outlier way up here, everything else down there. If you include that outlier, you've got this is your regression line. If you don't include that outlier, this is your regression line. Obviously, there's a pretty big difference between the two. In this case, you have a slight negative without the outlier, but when you include the outlier, you have a positive slope. So that's going to drastically change your results. So it's important to to look at your data before you start working with it. And it usually it's just enough to do the summary statistics, look at the mean, look at the standard deviation, and then the range of your data. If you've got a super huge number in the range of your data, like if you're doing income and everyone else is in like 50, 60,000, and then there's like 10 million. Not that that's wrong, but you're gonna want to drop that from your sample because it's not, I don't know, it's an outlier. It doesn't accurately represent the rest of the population. If you're working with state level data, and especially if it's per capita, Washington, D.C. is gonna screw up everything. I did a project on involving crime. So I was looking at per capita crime rates in each state, and I included Washington, D.C., and their crime rates were insanely high compared to everyone else per capita because it's so much smaller than all these other states.
In Rhode Island, though, they're not,
Rhode Island is a lot bigger than D.C.
they're not all over the place.
Likewise, if you're working with a panel of several countries for this project, I don't know, maybe comparing monetary policy across those countries, it's important to look and make sure that there's no extreme outliers. Oh yeah, and ask the question, is this loan point an outlier in X or Y? What do you guys think?
Why?
That's right. You can say this is like a plot of age versus sense of humor, and I'm the outlier up there with that awesome sense of humor. Thanks for the pity laughs. Okay, so going back to the problem of just including one variable as a predictor, the error term, that U that we talked about that we want to minimize, that arises because of factors that influence Y that are not included in our regression. Basically, there's always omitted variables. Oftentimes, they're omitted because, frankly, it's not possible to collect the data, or no one has collected the data yet. Other times, it's because we simply haven't thought of it. But if we don't include a lot of those variables, we're going to end up with a biased estimator. It's going to be inaccurate. It may even go in the wrong direction. So it's something we need to account for. And this is called, the proper name for it is omitted variable bias. So for the omitted variable bias to occur, has the omitted variable, or Z variable, has to satisfy two conditions. First is that Z is a determinant of Y. And the second is that Z is correlated with the regressor. Both conditions have to hold for the omission of Z to result in omitted variable bias. Obviously, the first part is, that makes a lot of sense. That Z is a determinant of Y. So the amount of time students spend studying affects their test scores. But the other is that Z is correlated with the regressor. So the fact there is some relationship between the amount of time students spend studying and the student-teacher ratio. Another example, the one that the text deals with, is English language ability. This is another thing that can plausibly affect standardized test scores. If you understand all the words, it makes it easier to answer the questions. Additionally, immigrant communities, especially this test was done in the state of California, or the data comes from the state of California. So immigrant communities tend to be less affluent and then have smaller school budgets because school budgets are partially determined by taxes. And they'll end up with a higher student-teacher ratio, less money to spend on the school. You're going to have fewer teachers. So in this case, Z, English language ability, is correlated with X. So that makes our coefficient that we estimated, the beta, that biased. What direction do you think This would a bias star estimator.
For the higher student-teacher ratio. Now, for the lower student-teacher ratio, or even lower test scores. Or we would have seen.
So you think they bias it upwards?
Sure.
Okay. So for our example, that's correct. That let's say districts with fewer students that speak English as a second language, they do better on standardized tests and have smaller class sizes. So if you ignore that, you're going to overstate the class size effect. You're going to overestimate it. That's not really a formula. I don't know why they called that a formula.
Great formula.
Yeah, does 1 and 2, does that help you? So getting back to our ideal, what we, in a perfect world, we would have an ideal randomized controlled experiment. First is that the ideal means that all subjects would follow the treatment protocol. There's perfect compliance, there's no errors in what they did. So say you give, you're in like a medical experiment, they say like take this pill 4 times a day at certain times, but you actually take it at exactly those times. You don't miss treatments or take them late or something. Randomized, meaning that the subjects of interest are randomly assigned to the treatment of the control groups. So there's no, I call them confounding factors. There's no other thing impacting which way people go. So let's say for that medical trial, we're dealing with weight. If you would have more heavy people take the treatment versus not take the treatment, you'll get a different effect than if you randomly select them. So you have, generally like the same people, the same weights on each, like doing each treatment. The next is controlled, basically that you have a group to compare against. So one group gets the treatment, the other group does not get the treatment. So not only do you see their effects before and after the treatment, but you can compare them to someone else so you can see how that changes. Because maybe over time, it's going to increase no matter what. If you're looking at historical data, maybe you're looking at inflation back when inflation was increasing, say through the 60s and 70s. And if you try to study that, you may say, oh, like this, whatever thing you're regressing on it, that caused inflation to increase because it increased over that time. But if you have a control group, you can compare that this other, say you look at Canada, who was also having inflation at the time, and they didn't undergo the treatment. You're then able to say, well, they both went upwards. So what's the difference in the trend after that treatment took place? And that's where you're getting your true effect. And finally, there's experiment. The treatment is assigned as part of the experiment. The subjects don't have a choice, so there's no reverse causality. There's the characteristics of the individuals aren't impacting whether or not they do something or whether they undertake the treatment. The treatment is forced on them. So how does our data differ from that? The treatment is not randomly assigned. So you may be looking at financial regulations or monetary policy. These aren't randomly assigned, they're purposely undertaken. In this case, the textbook example, the percent of English learners in the school district, it is not randomly assigned. The school district, obviously, I'd say immigrants seek out different communities. They go purposely to different communities. So the communities are going to have different percentage of English or percentage of students that speak English as a second language based on their characteristics. So there's 3 ways to overcome omitted variable bias. First is to run a randomized controlled experiment in which a treatment is randomly assigned. Like your medical trials, like you commonly think of for an experiment. You can also do a sort of what they call a cross tabulation approach, where you break up into different levels of student-teacher ratio and the percent of English language learners, and you can compare within each of those, in each of those little groups. But eventually you're going to run out of data, and there's still other omitted variables that we're not dealing with, just when you look at these now 3 variables. So the last choice, and so the stuff that we're going to be working with, is using a regression in which the omitted variable is no longer omitted. So you just include it. So here we have our new regression. I didn't get. For those of you who weren't here, last time I changed the beta zeros to alphas, just so the variables were different, so it was easier for you guys to keep up with. I didn't for the multiple ones. So I apologize if this makes it more confusing. But it's basically the same as we dealt with before. You have your y variable, beta 0, which is your constant. So if everything else in the equation was 0, that's what y would be. You then have your x variable, our variable of interest, and its coefficient, and then your control variable and its coefficient, plus the error term. The subscript I just means what unit it is, and the unit goes from 1 to n. So if you have 420 observations in your sample, you basically want to run this regression 400. I guess write that equation out. You're not going to write it out, but think it was being done 420 times. There's one for each of those, and that's how you basically how that calculates your coefficients. So when you're interpreting the coefficient you get, say your coefficient of interest, beta 1, it's going to be holding this constant. So you're only, if there's a change in this, in your variable of interest, this is going to remain the same. That way, you're actually getting the effect of, let's say, of what your variable of interest is.
Good question.
Yeah.
These downloads data off like
Stata costs money. So we in the lab in the basement, the computer lab, we have Stata for free, Stata 11, that you guys can use. I don't know how easy it is for you guys to get in there. Okay. Yeah.
in Caesar lab.
Yeah, you need I know you need a key to get in there, unless someone's already in there. I know the Caesar fellows can go in there anytime, but I don't know.
Yeah,
Other
but only
students
if it's unlocked.
Yeah.
So.
She didn't ask me, she was like, I wanted to get Chris for a few kids for this year. She was like, do you want access to it? She doesn't say.
Well, there's no swipe or key, how do we have access?
So just go in.
Yeah. Yeah. And then
Shut up. Or
I have a key, so I can, if it's locked, I could let you guys in if I'm here.
usually during night
So yeah, that's cut down on your ability to do it at night though. If not, I'll also show you how to use Gretel, which is free software you can download. But that's a lot more simplistic, so if you're trying, you can run a lot of complex models in macroeconomics because of all the different variables you're working with. So Gretel isn't the best source to use for that. If you're using a panel data set, then Gretel's fine. So I'll show you Gretel and Stata, the simple stuff to do. So you can use either of those for your project based on what you need. You have another question? Okay.
I'm gonna sign up for a free student short-term license request.
Oh, you can get a free one?
Should
Nice.
I put, you or Tim as the instructor?
Put me.
You guys have access to data set or no?
What do you mean data set?
Is it data set?
Oh, that does remind me. See if I can find it.
Link to your profile on your university website.
Fact set.
Yes, NBR has macroeconomic data on here. I totally forgot about this. Yeah, so there's a lot of data on here that you can get without having to build it yourself. Like go to Fred and download each variable you want and then combine it in Excel. You can go straight to the MBR. Yeah, so if you want to look at how all these okay, I'm not going to go through this. I'm going to get trapped and spend the rest of the class working with that. But I will put a link to that in the in Canvas, so that if you guys can check it out and see if those data sets will work for your whatever project you want to be doing, whatever topic you want to work on. A lot of times when people publish papers in like these like top journals, they'll put their data sets out there that they worked with, whether it's like on their website or with the like through the journal. So you can go through and get their data set and work with what they did. Or if you're working on your own project, you've just cut out all the work of actually gathering the data yourself. Which gathering the data can be a huge time component of any project. So if you find a source, that's great. I found a source for poverty statistics with like 80 or 90 different variables to look at, which I didn't have to do myself. It's for every state from like 1980 to last year, which makes me like so much easier than going to like the SNAP like website and downloading the data for each year and hoping they go back far enough.
How do you know it's correct though?
How do we know any of this stuff is correct, really?
True. So the place where I got that data from was from the UK CPR, like University of Kentucky.
That sounds reliable.
University. It sounds reliable. It was cited and used in other papers in the past. If it's been used in a journal before, that's a great way to know that that's a reliable source. You can usually get a feel by looking at like where it came from and who gathered it, if they attached their name to it, whether it's good or not. Okay. So now, this is the output that you get in Stata. The only difference from before is that we've added the percent for English as a second language. So we now have three coefficients: the student-teacher ratio, the percent English as a second language, and our constant. We see our student-teacher ratio, the coefficient is now lower. It was 2 point something before. Now it's 1.1, both negative 2 point something, negative 1.1. So we overstated the effect when we didn't include the omitted variable. And percent of English as a second language students also has a negative relationship with this test scores, as our theory would have suggested. Now, what did adding this omitted variable do to the significance of the student-teacher ratio? You guys remember what the p-value was before? Now we're up to 0.01.
Means that the probability of something is. Our model is not inclusive as much as before, right?
Is it better or worse that our p-value is now higher?
Worse.
Yes, it's worse. The probability that our coefficient is due to random chance has increased from 0 to 1%. So just over 1%. So we're no longer strongly statistically significant. We're just regularly, like normal statistical significant. So if you're, remember, if you're less than 10%, that's weakly significant. If you're between 10% and 5%, you're just significant. And if you're less than 1, you're 5% to 1%, you're strongly significant. Yeah, so never mind, we're still strongly significant. I guess 5 all the way down to 0. It's pretty rare to actually get p-values that are like 0.00 all the way down. Sometimes you'll see, wait. Okay, yeah, I knew I messed this up somehow. We're gonna end here once I finally get it right. This is 10 to 5%. This is 5 to 1%, and then this is less than 1%. I think that first one did look right. So, it's very rare to get strong statistical significance, like across your models. That's obviously the goal. A lot of times, the best we can do is get in this significant range. If you can get 1%, 2%, you're doing really well. If you're between 10 and 5%, it's weakly significant. It's not very good. It's still something to report, but it's not. If that's the best you can do, it's not great evidence in favor of your hypothesis. So now, the student-teacher ratio, our coefficient is negative 1.1. So what that means is if we hold the percent of English as a second language students constant, for every increase in the student-teacher ratio of 1 unit, we're seeing 1.1 point lower test scores. Because we're including that omitted variable from the first one, we're getting more accurate results. When you're writing a paper, it's usually, sometimes the authors will mention the effect of the control variables. Other times they won't. They'll only report the variable of interest, or they'll only discuss the variable of interest, because that's obviously what we're looking for, and you're just including the controls to make sure it's an accurate estimate. Sometimes it may be of interest. Maybe you find a statistically significant opposite effect than what you expected, and you can mention that. But frequently they'll just include, they'll include a table with all the coefficients and whether it's statistically significant or not, and then only discuss the variable of interest. You guys have any questions about multiple regression output? If not, then we'll end class